Facts. I'm Katie.
I'm Vinny, and this is Learn Real Good,
A podcast
about science.
where we introduce our guests and talk about their work. But first, we shoot the breeze and share some facts. That's what we're all about at Learn Real Good.
Oh, I like that voice.
Do you?
Meh.
It's my natural voice.
It's your natural speaking voice.
Yes, my speaking voice. So what's new, Vinny? What's on your mind right now?
You know what? It's been so cold. We're recording this in the early days of February, but for the last 2 weeks in Montreal, it has been just Arctic.
Yeah. Really cold.
Really bitterly cold.
Yeah.
The
nice.
wind is not cool. It is cold. It's being powerfully uncool.
Do you like winter in general?
I love winter in general. I love the
Okay.
snow. I love the sun. And it's a sunny winter. It's not like a cloudy, rainy winter. And when it's bright and sunny, you know it's cold, but if you stay inside, that's fine. But this is too cold. You can't even go out.
So my frame of reference for Canadian winters, I did my undergrad in London, Ontario,
Right.
and that was my least favorite of the winters because it was so wet all the time. And like walking through campus, there were just slush puddles all the time, and they used so much salt out there. I just remember like salt water wicking up my pants to like my knees, and then they'd be stiff by the time you're leaving class. And like I went through so many pants just destroyed by that saline solution, and I had to trudge through. I hated that.
Yeah, we don't salt our roads or streets.
No, we're
as
sand
much.
people.
Yeah, sand. We are the sand people.
And then there's Edmonton that does nothing because it's just too cold.
Right,
and not snowy enough.
You've told me about the ruts. The road ruts.
Yeah.
Because they don't clear their streets.
Well, so I did a degree in Edmonton, and a lot of the people I knew in my lab were from like Ontario, Quebec, and so the seasoned Albertans would have to explain the snow removal situation in Edmonton, which was they didn't. It snowed so infrequently, it didn't make sense to have all those snow trucks and such. So there'd be like a foot of snow in December, and you're like, when are they going to come plow this? And the answer is never. And so just over time, you sort of pressurize and compress it. So the roads get these like railroad tracks basically. So when you have to switch lanes, you have to like rev up. It's a wild ride.
You swing back and forth in the ruts, and you have to like basically jump tracks.
Yes, it's like it's the real Wild West when it comes to winter.
I mean, Montreal, it's cold, but the snow removal is top notch.
It's unprecedented. You have like crazy snows, and then you hear on the news like we have our 5-day plan. All the snow will be removed in 5 days.
Yeah.
It's intense.
Yeah, a whole city, like giant streets are all cleared of snow. Both sides, parking, everything. The whole snow just gets erased from the city. It's very impressive.
But also the trucks, like that is something I don't know.
The ballet of trucks and snowplows?
That needs to be explained because trucks come by before plowing your street and have this honk that sounds like a goose.
Oh, the tow trucks. The tow trucks. So yeah, the first step is tow trucks. If you are in a zone and your car is parked on the street where they're about to plow, the tow trucks come by and go wee wee wee, and it'll wake you up. It will rattle your bones. You cannot function as a human being while that sound is going on.
Yeah, but that doesn't happen. I've never been anywhere else where that happens. That's not a regular thing. It's very startling when you're new to this town.
And so then once they're done, any cars that are left there, if you haven't heard the alarm to move your car, they will tow it away. So I'm sure they tow hundreds of cars every winter.
Crazy.
And then the snow plows come. No, well, first the mini plows come to pile up all the snow into
it's a whole thing.
A large, like, little row of snow. And then the big plows come. And then the trucks go beside it so that the plow can put it in the truck. Then another truck replaces that truck when it's full. It's this whole process.
It's a whole thing.
Yeah. Anyways, that's amazing.
Yeah, there's movies. There's a documentary about it.
Is there?
Yeah.
Oh.
Of a Montreal snow removal?
I didn't know there was a documentary.
Okay, well, after this podcast, we have more homework. Yeah. But first,
yes,
we must continue what we've started, and that is sharing facts.
Fact time.
Who goes first? You.
You go first.
Oh, thank you. So my fact is an interesting one, and it led me down a bit of a wild goose chase. No, a rabbit hole. That's the one. A wild goose hole of facts and memories. But let's get started with the facts, shall we? So this comes out of a recent trial that took place in Malawi, where they have one of the highest rates of premature births in the world. And a fascinating way to reduce that, they found, was to chew sugar-free chewing gum twice a day.
Chewing gum.
Chewing gum twice a day, sugar-free, because the sugar brings its own suite of health issues. During pregnancy was linked to a drop in premature births that was statistically significant. Now, do you have any idea as to why that might be?
The chewing motion of the gum and the jaw relaxes the whole body.
Well, some people take their oral health for granted and think it's a cosmetic issue, but it has a lot to do with your immune system.
Oh.
And not improper and insufficient oral health will lead to infection. So what'll happen is if you don't floss, if you don't brush, if you don't take care of your gums,
Right.
that bacteria builds up, it gets into your bloodstream, it goes to your heart, it causes all sorts of serious health impacts and can travel from a pregnant woman to the fetus.
Wow.
Yeah. And this led me to remembering in the distant past as a child watching an Oprah episode where she had some specialist on who talked about like surprising things that have huge consequences on your health. And I just remember since then that like if you floss, that basically adds 4 years to your life compared to someone who's exactly the same who does not floss. Well, it's a difference of 4 years is the point.
All right. So I'm not going to add those 4 years.
Not
the greatest flosser.
We're not great flossers.
I'll floss here and there. Eat some corn. You got to floss.
Yeah, you're down for a post-corn floss.
You got to.
But we're not daily flossers. That's TMI.
Sorry, everybody.
Anyway, it was funny enough. I was able to find who this person was. I just Googled Oprah flossing, extending your life guy. And
you wanted to follow them on Instagram.
No, I was just curious. Anyway, I found them. Dr. Thomas Pearls, who's sort of famous for creating this list of questions that allows you to sort of determine your likely lifespan. And so I did that this afternoon.
Yes.
And I'm happy to report I will live till I'm 88, which I feel is
that's a good age.
That's pretty good.
That's a good age.
Yeah, so if an anvil falls on my head next week, I'm going to be pissed at this guy.
You can hold them responsible.
No flossing required. 88, I don't need to be 92. I'm good. If that's the difference. I'm going to just fill this with toffee.
Just replace your teeth as they fall out with toffee.
With chiclets. Yeah.
That's amazing.
Yeah.
What a great fact.
Wow.
So dental hygiene impacting infant birth.
What's interesting is they sort of
amazing.
controlled for, I guess, the potential of them being tipped off that chewing gum having something to do with oral health that might have led to other changes. They sort of gave the two sets, the control set and the people who were given the chewing gum, a lesson on proper oral hygiene. So they got the same sort of instruction, but one got gum to chew and the other didn't. And so it still had a significant difference. Anyway, I thought that was interesting. They're now going to try to extend it to other parts of the world.
That's very cool. That's a simple solution too. Just some gum, sugar-free gum.
Well, it doesn't fix the problem.
Fixed it.
But it reduces it.
Brought to you by Big Gum.
Trident. Making out like bandits here. All right.
You want to hear some other facts? Well, mine's a space fact again. I love space facts.
Yeah, I'll give you a space fact.
So you're familiar with the moon.
I've heard of it.
Yeah?
Yeah.
Okay. And it's a big ball of rock up in the sky. Now, the Earth... Yeah, you're laughing already.
So far, so good.
So far as you're following. Yeah, good.
Mm-hmm. Big rock.
Familiar with it.
Yeah.
The Earth is big compared to a person, but the moon is big compared to the Earth. Most moons aren't as huge compared to the planet that it orbits around, as big as the moon. Like the moon is bigger than some of the planets. It's huge. Pluto, not a planet, but does have like a very large companion body that orbits around it, not a moon.
Do we know their companions? Has that been verified?
Well, they haven't registered any at City Hall, but they orbit around one another.
Sure.
But the size of the moon has a huge impact on so much of what happens here on Earth, and a lot of scientists speculate that it may have like a significant effect on life developing on Earth.
Okay.
Two factors. One being the tides. Tides are controlled by the moon, and without a moon as big as the one that we have, the tides would not be anywhere near as strong. And so a lot of people believe that the moon and the tides set the rhythm for a lot of life cycles and circadian, not just the light of the sun and the moon, because that can alter over the course of the year, but also the rhythm of the tides, and that is much more steady over the course of the year. The second thing that it does is that it stabilizes the Earth's rotation.
Oh.
And so the Earth spins around once a day. Every day we do a full little wibble all the way around. But the axis, the North Pole that we spin around, North-South axis, wobbles. Yeah. There's a wobble to it. So like where it points right now is the North Star, but that changes and it spins. It's called precession. And so the spin of the Earth processes around another axis, but the moon stabilizes it. It would be much more spinny, like a top. Like a top, it starts to lose momentum. It wobbles a lot, and the Earth would be a lot more like that. So the fact that the moon is so big, it means that wobble is greatly reduced by the size of the moon. And so one of the things that's really cool is that researchers have been looking into how does the moon get formed? Okay. And so the Earth being roughly 4.5 billion years, that's our best estimate.
Everyone knows that.
And the moon being roughly 4.4 billion years, so just a little bit younger. Yeah. And the current leading theory is that something the size of Mars, which is about half the size of Earth, has smashed into a early version of Earth. And so this early version of Earth plus this body roughly the size of Mars together creates the mass of the Earth and Moon right now.
Gotcha.
And if you do other types of collisions, you don't get an Earth-Moon system. So that's what these researchers looked into. What if the Earth is bigger? What if the colliding object is smaller or bigger? What if one of them is made of ice instead of rock? And so the thing that smashed into the Earth was made of rock. And what they found was if your planet is too big compared to the thing that smashes into it, it just vaporizes it and you don't get a moon. You just get a bunch of dust and then it all falls down to the planet and you get no moon whatsoever. If the colliding object is too big, it just forms like small, tiny moons. So the colliding object and the object it collides into have to be just the right size to get an Earth and Moon system of that ratio. Otherwise, the moons are too small or you get no moon whatsoever. So Earth is in one of the very Goldilocks situations for the life that did develop here, which isn't to say that life couldn't evolve without a moon, but it certainly is likely to be a factor.
Now, I'm still hung up on something you said earlier.
Yeah, what is it?
The Earth and Moon was one rock?
Picture little Earth, little baby Earth.
Going around the sun. I appreciate that.
Yeah, and then something about the size of Mars, like, oh, I'm coming in, look out, they smash together. A bunch of it comes back together as the Earth. It's like, oh, hello, now I'm the Earth. And then some of it forms the moon. So those two bodies are from the sum of the body that was the Earth and the thing that collided into it.
Oh, interesting.
Yeah.
Wow. Good job, Moon. So you're saying you were pro Moon Appreciation Day, is what you're
saying? The
saying?
moon is incredible. Like, we wouldn't have it without a very precise series of events happening.
People don't know that Vinny has a giant moon tattoo that covers his entire back.
Yeah. It's from Majora's Mask. It's got a big angry face on it.
That's enough tomfoolery from us. It's time to talk to a proper scientist, shall we?
Yes, let's.
Okay, well, please introduce our guest.
Yeah, absolutely. Well, let's say hello to Emily McGaugh, who is currently a postdoctoral fellow in the laboratory of Dr. Nostro at the McEwen Stem Cell Institute in Toronto. She obtained her PhD in physiology from the University of Toronto this past fall. The focus of Emily's research is to understand how pluripotent stem cells can be turned into, or differentiated into, insulin-producing beta cells in the lab for patients living with type 1 diabetes. Emily likes running, competing in triathlons, and spending time with her niece and nephew.
Aww.
And fun fact about Emily, on her birthday, she runs the same number of kilometers as the age she is turning.
That's amazing.
That is pretty amazing. Hello, Emily.
Hello, thanks for having me.
Woo! Thanks for being here, Emily. Glad you could take a break from running to join us.
Of course, I'm happy to.
Wow, this research, this is complicated. I'm going to guess that Vinny doesn't know what a lot of these words mean.
I understood the word cells.
That's okay. That's all I understood too when I first started.
Real talk. Appreciate that. So how about we start with what is a stem cell? How is it different from a regular old skin cell?
Sure. So the type of cells that we use in the lab, they're called pluripotent stem cells. So pluripotent essentially means that the cells that we have in the lab can become any cell of the entire body. So these cells, you can get them from a variety of different sources. One source is that you can take them directly from an embryo. So as an embryo is forming, there's something called the inner cell mass. And it's the cells of the inner cell mass that are pluripotent. And again, pluripotent just means it can become any cell of the body. So you can either take these or get these cells from an embryo, or scientists have actually discovered ways to turn an adult cell, so an adult cell is something like a skin cell, and to revert them back in time to become pluripotent. Okay. So there are different ways to have pluripotent cells in the lab, and we have cells through both ways. So we grow cells that can become any cell of the body, but we specifically want to make the insulin cells.
So we will get to that, but I'm still hung up on these stem cells. So you differentiate pluripotent from other stem cells because some stem cells can't become anything? Like there's a narrow range of things they can be?
Exactly. So, well, there are different types of stem cells. So we work with pluripotent. The other is totipotent, which means it can become all cells of the body plus extra embryonic or like placenta. So we don't work with these cells, but a totipotent could essentially become an entire human being. Whereas the cells that we make in the lab, they can become every organ of the body, but not an entire human being because we're not making like the placenta. There's also another type of stem cell called multipotent, and this is restricted to the type of cells it can become. It can't become any cell of the entire body, but for instance, there might be a multipotent pancreatic cell, which means it can only become cell types of the pancreas. So it's restricted.
Right. So it's kind of like subsets. So you can have what's the first one? Totipotent is
exactly.
Like could be anything.
Yeah.
And then pluripotent and then multipotent.
You've got it, Vinny.
Okay, great. So they're like basically large sets that become less various sets of cells and then even less diverse types of cells. Okay, great. And so do we have all of these types of cells as adults, or do we lose them? Do we lose the ability to make these kind of stem cells?
So as an embryo develops, they start off as pluripotent stem cells. And as soon as these cells start to differentiate, and differentiate just means essentially grow or turn into something else. As soon as pluripotent stem cells start to differentiate as an embryo is developing, they lose their pluripotency. They still may retain, and likely do retain at very early stages, their multipotent capacity, but they lose pluripotency. They've lost completely totipotent. So the most they can have at that part is multipotent.
Okay.
But some cells may even lose multipotency and just become very restricted to the cell type they are.
And do we know, Emily, what is changing about a cell for it to change its potentness?
Yeah, does it just get
Is
lazy?
it a DNA change?
Is it tired?
A regulation of gene expression change? Like what is different about it? Do we know that?
Essentially all of those things that you mentioned, and a lot of research is going into figuring out exactly what's required to turn the pluripotent cell into the cell type of interest. There are a lot of changes going on within the cell, and a lot of research is going down into the nitty-gritty, trying to figure out which signaling pathways are regulating this process. So there are many different things that's going on during this time.
That's fascinating. It's like a student graduating, and then it's like, well, what field do you want to major in? And it's like, I want to major in biology. Yeah. And then it's like, I'm studying biology. And it's like, great, I am a biologist. And then we're like, no, we need you to go back and start over. We want you to turn into a civil engineer. And then it's like, well, no, I already studied. And so your job is to tell them, no, go back to being a grad student, and we want you to study civil engineering.
Exactly.
Emily lectures cells. That's what she does. She lectures cells. So you mentioned, Emily, that people have discovered how you can sort of go backwards in potency. How does that happen in very, if it's possible, basic terms?
So my research specifically doesn't look into this. I mean, when we use cells that, it's called induced pluripotent stem cells, so iPSC, so you're inducing pluripotency back into the cells. So there were scientists, Yamanaka, who discovered this. I think it was 2006. I'm sure someone can fact check that. But he identified transcription factors, so things that can change part of the cell to kind of revert it back into its younger self, in a sense. So they're transcription factors, and there are 4 main transcription factors that Yamanaka identified that you would need to add to your adult cell. So you add these transcription factors to your skin cell, and then it integrates into the DNA, and then it reverts back in time to a pluripotent state.
So that's like when you have, like, at least with an Apple computer, if something goes wrong or you delete a document, you can sort of reset it to the previous day and that restores the document sort of indirectly. Kind of yeah. Like that, right? I'm trying to get on Vinny's analogy train.
It's something probably very similar to that.
Okay, Emily said it's exactly that.
And so your specialty is insulin and the beta cells that produce them.
Exactly, yeah. So we're trying to figure out how to turn this pluripotent stem cell, a cell that can become literally any organ of your entire body. How do you specifically make not only pancreatic cells, but just the insulin cells that lie within the pancreas? So this process occurs in like women during pregnancy when they're growing an embryo or a fetus inside of them. This occurs over 9 months, and we're trying to do it in the lab in a much more efficient process.
Right. Wow. That's fascinating.
So yeah, let's talk about insulin. What's insulin?
Sure. So insulin is it's a hormone. So essentially a hormone it's like a messenger that tells your body to do something. So insulin is important because it tells our body to take glucose from our blood and give it to the cells of our body. So when you eat food that has glucose or sugar, so glucose is kind of like another name for sugar. When you eat food, sugar goes into your bloodstream. The cells of our body need sugar to function. So we can't survive without glucose, without sugar. So insulin will tell the cells to take the glucose from the blood. So when you have type 1 diabetes, you don't produce insulin. So if you can picture what's going on, if someone has type 1 diabetes, they're eating food, sugar is going into their bloodstream, it's staying in their bloodstream. The cells of their body are not taking this glucose up. So what this means is that the glucose is staying in the blood, so they have high blood sugar. So hyperglycemia.
So basically, it's like when you're in the office.
Here we go.
Here we go, analogy time.
I'm ready.
It's when you're in the office, it's Joanna's birthday, there's cake in the communal room, and everyone's like, there's an email that goes out. Hey, everybody, there's cake in the room if you want some.
Watch out.
But if you don't have insulin, you don't get that email. You don't get to have the birthday cake.
Let's cut that one. That's tricky because cake is also something that will cause your insulin to spike.
But I mean, the cells are the people in the office, and they don't get to have the cake if they don't get the email.
I don't think we're quite there. Emily, can I ask why? So having this sugar build up in your bloodstream, do you know why that's bad? Is it more that it means that our cells aren't getting the glucose they need to make energy? Or is it more that sugary blood in and of itself is bad, like it becomes all thick and doesn't move? Or is it both or neither, or what's going on?
I'd say it's both, but sugary blood or hyperglycemia can lead to a number of complications such as kidney failure, blindness, amputation even, and sometimes even death. So insulin was discovered 100 years ago, but prior to that, when children had type 1 diabetes, a lot of them would die quite early on because you can't live with high blood sugar.
Fascinating. And so there's a type 1 diabetes and there's a type 2 diabetes.
Right.
So let's talk about the distinction
Sure.
of those, because I don't know them.
So type 1 diabetes actually accounts for about 5 to 10% of all cases of diabetes, whereas type 2 diabetes accounts for about 90%. So the prevalence of type 2 is much greater. So like I said, type 1 is when patients, they're not making insulin. For type 2, they're making insulin, but they're not using it properly or they're not responding to it properly. So there is quite a difference in terms of how these diseases essentially exist. And so what we're trying to do in the lab when we make insulin cells, primarily we focus on type 1 diabetes just because insulin is their only source. They use needle or they inject themselves with insulin. But we also think that insulin cells could also be helpful for some people who live with type 2 diabetes who are also on exogenous insulin or who also are injecting themselves with insulin.
And would that be because, well, if you have type 2 diabetes and that's because for you, like the receptors or whatever on your cells aren't super great, by getting these new beta cells that you make, it sort of suddenly will jumpstart a response? Or
we don't think it necessarily will change the receptors that are responding to insulin. I think there are other drugs and other researchers that focus on that to make cells more sensitive to insulin. But if a patient requires insulin injections and our cells make insulin and can regulate insulin accordingly, then we think that our cells might be able to help patients with type 2 diabetes.
That's amazing.
But primarily our focus right now is type 1.
Yeah, and so how do you do it?
Yeah.
How do you turn, first, how do you get a cell? How do you turn it into a stem cell? And then how do you make that stem cell into a beta cell?
So I guess the thing about stem cells or pluripotent stem cells, they have two unique characteristics. One is that it can divide indefinitely. So you have one stem cell, it keeps dividing. So theoretically in the lab, we have an unlimited supply of stem cells.
Nice.
So the source of stem cells for us isn't a problem. And in fact, a lot of the stem cell lines, and by stem cell lines, I mean, because pluripotent stem cells come from either an embryo or like an adult cell that's been induced to generate, these are different lines. So one embryo is one stem cell line. You have another embryo, that's a different stem cell line. So a lot of our stem cell lines, we actually received, or we have had for about 30 or more years. So these cells, they keep duplicating. We're not going to run out of them. The other characteristic is that, like I said, they can become any cell type of the body. And this is where it becomes tricky. And this is what part of my thesis was focused on, is how do we do this? How do you take a process that takes 9 months during human development? And right now, scientists in the diabetes field are able to generate insulin cells in about 15 to 25 days. So we're trying to like speed up this process and figure out exactly what's required to make them.
And so I guess, how do we
make them?
The 15-day, what's the 15-day process? Is it like cheering them on and be like, go stem cells?
Right. Yeah, I definitely do that, although I'm not sure how helpful that is, but I do that. So what we do in the lab, and a lot of this work is actually, like, I was lucky to come in during a time when scientists before me have already discovered how to make certain cell types. So there are 3 different germ layers that make up our body. So 3 different types of cells that make up our body. And the 3 of them are endoderm. And endoderm is like all the internal organs, like liver, lung, pancreas. So I'm interested in endoderm because endoderm gives rise to the pancreas. The other is ectoderm, which gives rise to like nerve cells or skin cells, and then mesoderm, which gives rise to muscle or kidney or the heart. So what we try to do is we take our pluripotent stem cells through stages or steps of development that would normally occur during human development. So the first step is to make either endoderm, ectoderm, or mesoderm. So there are scientists before me who discovered ways to do this, and they found out strategies to do this by studying other model organisms like mice or chicks. And the reason is because for ethical reasons, it's very difficult to study human embryonic development. So a lot of the ideas that scientists had before me was to study, let's say, mice. So they would figure out, what are pluripotent stem cells in mice? What kind of environment are they experiencing to turn a pluripotent stem cell into endoderm or mesoderm or ectoderm? When I entered the lab, we were already able to make endoderm. So that's that first step. Then we start to specify into the different organs. So endoderm, just for simplicity, endoderm can give rise to the stomach, the pancreas, or the intestine, as well as many other organs. So at some point, a cell is going to need to decide, is it going to become the stomach, the pancreas, or the intestine? So scientists are then looking at mice, looking and trying to figure out what different proteins, what different environment is a cell being exposed to that allows them to be pushed towards the pancreas as opposed to the stomach or the intestine. So in the lab, we test lots of different proteins. We activate or inhibit different signaling pathways. So we kind of try to change what's going on within the cells to figure out how to turn them into pancreatic cells and then how to turn them into insulin cells.
Wow. So it's a bit of like a Wordle.
Yeah, except we get a bit more than 6 tries.
Thank goodness for that.
Yeah.
Okay, and so what happens after you successfully convince them to be pancreatic cells and specifically beta over the alpha cells somehow? Now you have a pile of cells. What do you do then?
Right. So I think it was around 2014, scientists have developed or came up with a protocol that was able to generate a relatively efficient number of insulin-producing cells. So since 2014, we've now been able to make insulin-producing cells. But as we begin to develop technology, we've tried, or we now have new technology that's allowed us to study our cells better. So as we make these cells, we also need to study them to make sure they are in fact proper insulin producing cells. And these cells are called beta cells. So beta cells are the cells that make insulin in the pancreas. So although we can make insulin cells, sometimes these cells express other things that we don't want, like glucagon. So now we're trying to figure out exactly what type of insulin producing cells we've made, and we can test them, so we can characterize them in vitro, which means in a dish or in the lab. So we have, you can do something like single cell sequencing. So you look at a single cell level and try to figure out what each cell expresses. You can also look at how the cells function by putting them in a mouse. So we're starting to figure out exactly what type of cells we are making. And as a result of all of this effort that's going into figuring out what we have made, clinical trials have now been launched to see how these cells function or how they develop and grow in humans.
That's wild.
Yeah, this is amazing.
So what was sort of the end of your thesis? You're like, here's the petri dish of cells. Like, did your thesis go into installing them into mice or humans?
So for my thesis, my main project was to look at one specific protein. So there are thousands of different proteins to look at. I looked at one of them at one specific stage of development. So if making insulin cells is a 7-stage process, I looked specifically at stage 3 and at one protein. So my project actually was to figure out how a cell, or what dictates whether a cell becomes a stomach, pancreas, or intestine. So I looked at this one protein to see if I stimulated it, did it become a stomach or a pancreas? And if I inhibited it, what happened? So that was the main work of my thesis. And then I have side projects where I try to generate essentially more insulin cells in a dish.
And what was this magical protein? Was it like a structural component of the pancreas, or what was it up to?
It's called FGF, so fibroblast growth factor. I know that probably doesn't mean too much for anyone listening, but we found that this protein was expressed by pancreatic cells. So in research, you find a protein, you see that your cells express it, you don't know exactly what it does, so you figure it out. So before I looked into it, we didn't know what it was going to do, but now we just know a little bit more about it, but still not everything.
That's awesome. Well, we need to give work to the future generations, right, Emily?
Exactly. I didn't want to steal the excitement from someone else.
Yeah. You can't do everything.
You can't.
And do you have like a big framed computer-generated image of this protein on your wall?
Not yet.
Let's fix that.
Yeah.
Wow. And so you got into this research for a personal story, eh? Emily, do you want to talk about that?
Sure, yeah. So when I was in undergrad, I was at York University, and I did in biomedical science. So I liked science. I wasn't a huge fan at the time of research. I guess I just hadn't really been exposed much to it, or like high school research experiments weren't very exciting. I feel like we had a styrofoam cup, bit of water. I'm not quite sure what was going on. But during my first year of undergrad, I remember my mom phoned me one day and she said my sister was just diagnosed with type 1 diabetes. I had no idea what this meant, like literally no idea. I think it had something to do with insulin, but I still wasn't sure. So since that day that I found out my sister had type 1 diabetes, I then tried to learn as much as I could about type 1 diabetes, which then brought me to learning about different research that was ongoing. And that's actually when I was introduced to Dr. Nostro, which is my current supervisor. So I met Dr. Nostro, I guess in, I don't know what year it would have been, maybe like 8 years ago. So I approached her shortly after my sister was diagnosed, and I started in her lab as a summer student, and then I've stayed in her lab ever since.
Wow.
So great.
What a beautiful story.
Yeah.
And a nice reminder, too, to any listeners out there that you never know when the inspiration will strike, right? You didn't go into university loving research and knowing you wanted to do that.
Exactly,
right?
Yeah. And unfortunately, I told my sister I was going to cure her diabetes, which is why I still haven't been able to leave the lab.
It's a bold claim.
Well,
I was so naive at the time. I should have been careful.
Every year on her birthday, she's like, Emily.
Yeah. Every year we celebrate the day she was diagnosed with diabetes. So it was 10 years this year. So every year she looks at me and wonders when the cure is coming.
Yeah.
No pressure.
Watch.
Wow, well, you're trying. I mean, by all accounts, you're doing the best you can with this.
You made progress.
Most people who'd make that promise have done nothing.
Like my brothers.
Yeah, what have they done?
Exactly.
I love this family. All the McGaughs were like, no, I'm going to cure it. All right? I'm not in science at all, and I'm going to figure this out.
That's awesome.
Amazing. And so you've moved on, you've finished, you're a doctor. What are you working on now as a postdoctoral fellow?
Well, of course, still trying to cure diabetes.
Yeah, but your sister
Were you
won't
not
let you
listening
forget
to me?
that.
I just said we didn't cure it yet.
Right.
Yeah. You're not done.
No, but so I'm finishing off. I need to publish my work from my PhD, so my thesis. So I will publish that shortly, and then I'm trying to figure out what to do next. So I'd like to still be involved in science in some way, and hopefully helping scientific discoveries get pushed to the clinic.
Can we talk a little bit about the difference between a thesis and publishing your results? So you've done your PhD.
You sound like my mom right now.
Yeah, well, I mean, there are people listening to this who probably don't know the difference of like what that means. Because let's talk about what a thesis is and why you have to publish it afterwards.
Sure. So when you're in science, you're trying to publish papers. So a lot of your research, or as much of your research as possible, you want to publish in papers, because this is what the majority of the world, or whoever wants to read scientific papers, is going to see. That is what your goal is. And now as a postdoc, that's my goal as well. As a postdoc, I don't have a thesis project. I've already done that in my PhD, so I'm not focused on a thesis. But when I was doing my PhD, your goal to graduate is to generate a thesis, which is a wonderful 200-page document that everybody wants to read.
Yes.
And so in order to graduate, I had to write a 200-page document. That's my thesis. Within my thesis are experiments that will then be published in a paper in journals, in a scientific journal. So the experiments that were done and will be published in both are very similar. They may have different styles of they definitely do have different styles of how you write them and how you kind of tell the story or scientific story. But yeah, so it's just, the thesis just really belongs to something that's specific to a PhD or like a master's.
Yeah, because you basically have to like tell the school, like, here's what I did. And the school's like, you did a great job. Here's a degree.
Exactly.
But no one really outside of the school really gets to look at that because it's not published anywhere.
Well, they will get published online, so they are actually available.
Yes. But people look at the journals. Primarily
the journals will be looked at, and part of the reason is, or maybe it's because they need to be like peer reviewed or edited. So my thesis, I did have a committee who read my thesis, but there are other people. When you publish a journal, one, the journal needs to accept it, and two, there are reviewers who will review your scientific work. That process isn't applied to a thesis.
And so you're in the process of organizing the stuff that you did for your thesis into papers to submit to journals, which will then be hopefully accepted, then reviewed, then you'll do an edit, and then it will show up somewhere.
Exactly. So I'm taking my 200-page document and putting it into 5 pages, maybe.
Yeah, that's tough.
Yeah, it's quite the long journey, and then it's once you submit it, it's months to hear back, and then months to get revisions, and then the whole thing. It's like kind of like movies. I always compare it to like actors are in a movie, and then the movie comes out years later. They've been, mentally they've been physically way past this project. Yeah. Exactly, but the rest of the world has just been enlightened to it.
Yeah.
So are you dead set on diabetes? Like, there's no getting Emily off of this horse until it's
not
resolved.
Getting her sister off of this list.
I'll need to convince my sister, but I think I can move elsewhere as well.
Okay, good.
But also, it's good to get experience in different scientific fields as well. Just let's say another field is making like cardiac cells, so heart cells. You can apply techniques you learn to make pancreatic cells into how you make cardiac cells. And I feel like you learn more, and the fields can progress a lot better if you learn from each other. So even if I end up in diabetes 20 years from now, I think it would be good to get experience elsewhere.
Totally.
All right, so Emily's sister listening out there, okay, so if she moves on, forgive her.
Prepare yourself.
Yeah.
One of our very first guests was someone who was turning stem cells into heart.
Oh, that is true. Building hearts. That was our first episode.
Right.
Whoa, full circle.
Well, this is
the end of our second
this should
season.
be the last episode
Whoa,
of our
that is
second
wild. We
season.
did not plan that.
Yeah,
I mean, we planned that.
But yeah, it's amazing. So this idea of using stem cells to kind of like fix things that are not functioning as they should be, like being able to get cells from someone's body, revert them into stem cells. Is it easier to do that than to just, like, when you have a baby, just grab some of their placenta and just put it in a library of stem cells? Is that a thing? Like, or is it just like, nah, just here, give me your hair, we'll make some stem cells, no biggie?
So a lot of the struggle that we deal with is trying to figure out how to turn the stem cells into the cell type of interest. And a lot of this requires on the quality of stem cell that you start with. So placental cells, it's difficult to determine right now how pluripotent they actually are and how well they can be turned into different cell types. There's a lot of research going into that, but my research, we've never used like placental cells.
Okay.
And so, yeah, we're just trying to essentially regrow organs in a dish, because let's say you're unable to have enough through cadaveric donors, we just think that this is an alternative way to make new organs in a dish.
I mean, it's great for people who didn't save their placenta.
and sure, yeah, they may have uses for other things, but we in our lab at Dr. Zanostra's lab, we just haven't focused in that.
Sure.
So would this sort of strategy of using stem cells to make tissues be mostly used for like organy type things? Like skin is pretty easy to get a skin graft, right? There's no reason. Is there any motivation that you can think of for figuring out a way to make skin cells from stem cells, or that's just like, well, that's an easy one?
No, there are definitely labs that have looked at making skin cells from stem cells, and for patients who experience like a lot of burn or like a high degree burn, so a lot of their skin has been taken off, patients have actually received skin cell transplants from stem cells. I think there was a paper maybe 4 years ago that was published, and they had turned pluripotent stem cells into skin cells, and they had used it to transplant on a boy who had experienced severe burns.
Amazing.
So yeah, it's amazing just the different fields that are present because of the ability of stem cells.
So is there a body part that will be especially difficult to generate from a stem cell?
Everyone who makes a specific cell says their cell's the hardest to make.
Yeah,
so
okay.
It's the beta cell, the insulin
Right,
cell.
yeah.
Correct answer.
Correct answer.
Correct. We agree. We're gonna push that forward.
That's it. Yeah, I can just imagine like taking a cell that could be anything and just like nudging it down that path all the way to one specific body part. Exactly. Or cell, not even a body part, just one cell in a body part.
But also like how much we don't know. That's fascinating, right? Like you had it down to like 3 tissues and you're like, this cell has this protein but not this protein. I guess that's somehow tied to it and we don't know what it's doing, but it's so fascinating. We always think, I think people outside of the work you're doing, we assume we know what every protein's up to and what all the proteins are, but there's so much still to be discovered.
Exactly. And even when we started to make insulin cells, or when the field started to make insulin cells in 2014 and 2015, they expressed insulin, but they weren't as mature or as functional as a primary insulin cell. So what I mean by that is the cells that we grew in the lab at the time, they didn't function like the insulin cells that are in you or me, assuming that we're healthy. So it's over time that we, discovered they weren't as functional as we thought, and then we had to figure out how to make them more functional. So we're always learning about the cells that we're making.
No kidding.
Very cool. And so where do you see your future, Emily? Are you always going to be in the lab playing with some stem cell or other, or do you think you want to teach, or where do you picture your life in 10 years?
I'm not sure exactly right now. That's what I'm trying to figure out in these next these next few months and years. I do really enjoy lab work. I do love turning stem cells into different cell types. So we'll just have to figure out and see what I
Sure.
continue to like in the future.
Very good point. You never know, right?
Yeah.
Life's a journey.
Yeah, I mean, hopefully none of your siblings get sick with anything else.
I
Then they'll be like,
know.
all right, Emily, gotta go back to the lab.
That will dictate my next career choice.
Yeah.
Yeah, perfect. Yeah, there you go. Oh boy. Wow, very cool. And so you're into like running and
Yeah.
triathlons. Talk about what it's like to run a triathlon, because honestly, we've not come close.
No.
So in my undergrad, I ran for my school, and then when I got injured from running too much, I then started to
Oh.
cross train, which involves biking or swimming. And I figured since I'm running, biking, and swimming anyways, I might as well try out a
You're already
triathlon.
there.
So they're actually a lot of fun. They're tricky, but they
We
are a
have
lot
different
of fun.
definitions of fun. But
Uh,
I'm glad you enjoy them.
yeah, they're great.
Which is there one of the events that you like hate? Like when you're running a triathlon, you're like, ugh, this one.
Yeah. So my favorite is the run, although it's the most stressful for me.
Okay.
And my least favorite is the bike. I find that so many people in triathlons are really good at the bike, but it's definitely not my strength. And you're not allowed to draft off people, so you can't even like tuck behind and yeah.
Really?
So
How do they keep that from happening? They're
You
like
have
too
to-
close.
it's like COVID rules. You have to keep a distance from the bike ahead of you.
Fascinating.
Mhm.
And so, what are the distances in a triathlon? So, swimming, biking, and running.
So the Olympic distance is a 10K run. I think it's a 40 bike and a 1 or 2K swim. My focus is the run. For the bike, I'm pretty sure it's 40, but it could also be 50.
Is it in that order too? Run, bike, swim?
No, you start with the swim. I think it's for safety reasons, so you're not exhausted and thrown into the water at the
that
end.
makes sense. Yeah.
Good point. Or you want to cool off at the end.
Honestly, I would have preferred to swim at the end for that reason as well, just to go for a cool off. But it's swim, then bike, then run.
So you come out, you just swam.
Yeah.
You come
A
out
kilometer.
wet. Do you just like get in that wet outfit? You just hop on a bike?
Yeah, so well, you start in a wetsuit, so like a full body like thing that's stuck to you. So as you're running out of the water, you're supposed to take the wetsuit off as you're running.
Oh.
I'm not that good, so I get to the transition zone, then I take the wetsuit off, then you hop on a bike, put on your helmet and stuff. And then after and you got to put on running shoes as well, and then you drop your bike off and go for a run.
Wow.
That's amazing.
That's very cool.
Yeah, so lots of people
Good for
spend
you.
time practicing the transition zone. So as you transition from the swim to the bike to the
Yeah.
run, I'm terrible at transition. My dad is like, Emily, what were you doing in there? Your makeup.
Wow, and is there like a good time for a swim to bike transition?
Definitely, probably a quarter of the time I take in the transition zone.
Well, taking off a wetsuit and being under pressure to do it
And put on
quickly.
shoes?
Exactly.
Cool.
Yeah, shoes while your feet are wet. It's just
Ugh.
tricky.
I remember I had to wear a wetsuit. I did a lot of scuba work for my PhD, and I would have to drive between like two sites, sometimes a couple of hours. And I would I'm not taking this off, because like taking off a wet wetsuit, and especially putting a wet wetsuit on,
Yeah, it's really
not happening.
Honestly, sometimes I feel like the hardest part of the triathlon is putting on the wetsuit at the beginning. I get help for that part.
Yeah. It
It's
should
not
be
great.
a quadrathlon, really.
Honestly, I think so.
Gotta time this part, too.
Oh my gosh. Well, thank you so much, Emily. Thank you for doing the hard work you're doing. Obviously, great research, and hope you keep chasing those
amazing
passions.
stuff.
Well, thanks a lot for having me. It was great to talk to you.
Awesome. Wow.
Thank you.
That's incredible.
Yeah, stem cells, like, it feels like treating the body with stem cells, just like, it's like when your car breaks. Here we go, analogy time. A car breaks, and you're like, okay, I could just get a part from the junkyard and replace that part.
Yeah.
Or I could just go to the car manufacturer and be like, I need this part, and you get the actual part that you need. And so stem cells is just like, hey, let's just go to the body, grab a stem cell, grow a new piece, slap it back in, you're good to go.
Well, I think of like that food generator from Star Trek. I know there's a
Ooh,
word.
yeah.
What's it called?
Replicator.
The replicator, right? You just I want exactly this. And it just takes this goo, I imagine, is in
Yeah,
that
a goo.
machine.
Yeah.
Some sort of goo.
Yeah, like a 3D printer.
I just have this, I didn't watch a lot of Star Trek, but I remember one episode where like this amazing sundae comes out. So like that's what I'm picturing.
Right.
We're calling this. But it's like the same goo that'll make a sundae or a steak or whatever you want, right?
Yeah, or a liver or a pancreas.
Yeah.
Yeah.
That's incredible.
Yeah, amazing.
Very cool.
It is very cool. This is the research that's being done now, it does feel like science fiction in some ways.
Yeah, it's unbelievable. Yeah, I know. I wish I would have heard. I wish this podcast existed when I was a youngin. I had no idea these things were happening when I got into science.
Well, let's hope youngins are listening to this.
Okay, youngins out there. Well, it's time for bed, youngins. Let's say thank you to Emily.
Thank you.
Thank you for sharing your facts about the moon.
Yeah.
I'll celebrate Moon Appreciation Day thinking of you.
Yeah, and thank you for all the winter discussion we had.
And the gum fact.
And gum facts.
That was the proper fact.
And the winter stands out more.
Great. Well, thank you for listening.
Thank you, listeners.
Send them out on our socials, Vinny.
If you're interested in following Learn Real Good on social media, you can check us out on Facebook, Twitter, or Instagram at LRGPod. That's LRGPod. And if you're interested in being a guest on Learn Real Good, send us an email at learnrealgoodpodcast@gmail.com. Learnrealgoodpodcast@gmail.com if you have some cool science to share.
Don't be dissuaded by the way he mentioned
Only cool science, please.
All right, that's enough. Bye, Vinny.
Bye-bye.
Bye, learners.